In the third problem, we have two situations. We have a before the moving part, in which we have what is known as static friction force, and then after we start moving the crate, we have what is known as a kinetic friction. So associated with a static friction is a static coefficient of friction, and associated with a kinetic friction is a kinetic coefficient of friction. This will become handy as we solve these problems. So if we look at before the moving of the crate, so nothing is moving, we know that the sum of the forces has to equal 0. And if we look at the free body diagram, we know we have the tension to the right minus the static friction force to the left, so this has to equal 0. This implies that the static friction force is equal to the tension, and we're given that the tension is 230 newtons. So we know what the maximum static friction force has to be. If we do the sum of the forces in the y equals 0, we have the normal force, which is the force that prevents the crate from falling into the pavement or the road, minus the weight, and that equals 0. So this tells us that the normal force is equal to the weight, and we're told that the weight is 500 newtons. So we found, by applying these forces, force summations I should say, we found the two other missing forces on the crate. And now the maximum static friction force is going to equal to the coefficient of static friction times the normal force, which means that the coefficient of static friction is going to be the friction force maximum over F sub n. This maximum friction force is what we are pushing against in this case just before it moves. And if we plug these in, we have 230 newtons over 500 newtons, which gives us a value of 0.46, no units. Whenever you're doing these problems, if you ever get a static coefficient of friction bigger than 1, you've done something wrong. It always has to be between 0 and 1, which this is. So that tells us that we're doing something correctly here. If we look at after the crate moves, this means we have the second free body diagram, or this one. And notice now the change is that instead of F sub s, the friction force is not static anymore, but it's kinetic. This will give us that the tension minus the kinetic friction force equals 0, which implies that the kinetic friction force is the tension, and notice now the tension is no longer 230 but just 200. And if we do the sum of the forces in the y direction equals 0, that tells us the normal force minus the weight equals 0, which implies that the normal force is the same as the weight, which is still 500 newtons. So notice that just because we moved, the weight is not going to change. And similarly to what we've done before, the kinetic friction force will be the kinetic coefficient of friction times the normal force. This gives us that the coefficient of kinetic friction is the kinetic friction force over the normal force, which is 200 newtons over notice that the kinetic friction in this case is smaller than the static coefficient of friction, and you'll see that is always the case. If you try to push something that's not moving, once you get it moving, it's a lot easier to move than when it was stopped, and that's because the coefficient of friction now for the kinetic is usually smaller than the static